Hi there, students. Welcome back. We're in lesson 14, video B. What we're doing is we're modeling the sample proportion. So in the previous video, Kim Shepard introduced the problem. The problem was that at Cecil, we have a hunch that maybe more than 20% of all students are smokers. The nationwide percentage is believed to be 20%. So in statistics, what we're moving towards is, let's test our hunch. Let's collect some data and see if my hunch is correct, that there's evidence that more than 20% are smokers at Cecil College. So we're going to demonstrate this with a simulation with a box of beads. So number one in your notes, I've got a box of beads. They're many colored, white, black, green, red. We'll show you in just a second. There's over 2,500 beads in the box, and those beads represent Cecil College students. Okay. The green colored ones are our smokers at Cecil College. Every other color is a non-smoker in the box of beads. Now again, just like at Cecil College, we have no idea of the true proportion of green beads in the box. Who's going to count these? There's over 2,500 of them. And just like at Cecil College, we have no idea of the true proportion of smokers for the whole college. Now the way that this works, and sort of from now till the end of the semester, what we have to do is we have to start somewhere. We have to start with an assumption. And so at Cecil College, we're going to guess or assume that it's 20% smokers, because that was what the national proportion is. Okay, so we're going to start with that, collect some data to see if we can refute that, because we do think it's higher. Number two, we'll show you in just a second. I have a box of beads, and then there's a paddle, and with the paddle I can just scoop 100 really quickly, and the 100 is simulating our sample size of n equals 100 students. We're going to take multiple simple random samples of 100. We're going to count up the green beads representing the smokers, and then each time we're going to figure out what proportion in the sample were smokers. So what percentage were green out of 100. We're going to do this 10 times. It might take a few minutes, but we'd like for you to get the idea of this taking repeated samples. Remember, in practice, we're not going to take 10 samples and see what happens. We're going to take just one sample, and we're going to have to rely on the theory, the statistical theory, to help us develop the ideas for the rest of the course. Okay, so this lesson 14 is all the theory stuff. We have to think and we have to imagine what would happen if we simulate. All right, so in the notes, you've got these boxes where we're going to put the 10 results from our 10 scoops. Okay, we're going to switch to the box of beads. Kim Shepard's taping. She'll write them down for me, and at the end, I'll come up and fill this in. So just hang tight on the notes. Unless you want to listen to what I'm saying, you can write them down, but I'll put them all at once. All right. So here's the box of beads. If I tilt this up, hopefully the camera's picking up the colors. You can see we've got quite a bit of smokers in here, right? The green ones are the smokers, white, pink, and purple non-smokers, black non-smokers. I guess there's some blue and yellow and stuff. All right, so we're gonna, shake up the students. Watching the video, you're in here. I mean, your bead is in there somewhere. Here's the paddle. It's 10 by 10, so there's 100 slots. And the way that this works is just scoop it in, and you'll get a random sample of 100, and we'll count up the greens, and that's going to be simulating one sample. All right, so we'll just sort of go in there and get it. You can see the results on the video there, and now I've got to accurately count this. So 1, 2, 30 greens. So the first sample, luckily, I mean, that's what, when Kim did the first video, she said, oh, what if we had 30? Here it is, right? So maybe we got lucky. I doubt we'll get that happening again, right? But in practice, we'll never do this. But for simulations, dump them in. We're going to shuffle up the population here. Go in, get a second scoop. And so here's our second sample. I'll count these up again. Second sample, 30 greens out of 100. It's not supposed to do that. We'd expect some variation. Maybe we'll set some kind of statistical record here. Here's the third sample out of 10. Sort of looks, it just looks like 30 again, but here we go. I'll count them up. $30. 3 in a row 30s. This reminds me of in Atlantic City, I saw the news story a couple years ago. A woman held the dice and craps for record for like 3 hours straight. I think we're getting that lucky here today. Good, here's a, ooh, looks like a lot of greens that time. So here's our fourth sample. I'll count them up here. $36 that time. So 36% smokers in this fourth sample. Finally, we get some variation. I guess at this point, remember that we're presuming 20% are smokers at Cecil College, but we're collecting this data. We haven't gotten any near 30%, right? Our hunch was that we had more smokers at Cecil College. Here's the fifth one. Let me count up the greens again for the smokers. $38 that time. 38 greens, so 38% smokers. Is that 5?
Yes.
All right, halfway done. And again, some things to think about. In practice, we'll never do this. We'll take one sample. We'll have to get a good sample and just run with that. And sort of what this chapter is about is, how can I make the most of my one sample? What does the theory tell me? What conclusions can I make from my one single sample? We're trying to understand the theoretical distribution if we did this multiple times. All right. And a good old swirl here. And here's our sixth one. $23 that time, so only 23%. Smokers, you can start to see that variation, right? Never had anything below 20%. So, all right, here's sample 7. All right, count up the greens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 only. 22 greens. And so we've had a low of 22% smokers. We've had a high of 38% smokers. All right, a couple more to go. Remember, there's 2,500 beads. Those are the students. Here's got a bunch of greens to start here. All right, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 27 that time. So you can see the variation. What do you think what would we expect? How many greens would we expect to get every scoop? That's something to think about. All right, 2 more to go. One student refused to answer there. Get another one. Scoop 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 30. So we're back to the 30s again. 30%. All right, last one. $31. All right, so we'll get these in the notes. I got them on paper. All right, so in the middle of the page, you've got those boxes we've done this, we've done it by hand. So you can imagine in the computer age, what if I wanted to take like 1,000 samples? We'd have to resort to technology, right? A computer could probably do this really quickly. This whole column, these are all p-hat values. So rather than write p-hat 10 times, maybe you want to label p-hat here off to the left. And so remember the first time, I'll use decimals. I mean, here's 0.30. This 30% is a percentage, but we'll typically be working in decimals for the calculations. When you get to the summarizing, write a sentence at the end, you probably want to go back to percentages because it's more understandable. All right, so we have 0.30. Second one, 0.30. Remember, we started to wonder about our box of beads there. 30, 30, 30. 36, 38. And then I don't know where the greens went, but 23. Sample 7 was 22%. 27%. 30%, and then 0.31, 31%. Okay. We did it 10 times. At 10 times, can I start to get a sense of maybe what's the mean? What if I did this 100 times and then calculated the mean of these proportions? I sort of might understand where's the center. Can I start to understand the variation? I think I can, right? It looks like these might be centering around 30%. And, you know, I jump up 6, 8, I jump down 8, 7. So standard deviation might be a couple percent, right? Maybe 2, 3, 4% for this problem. And just think about that. The ideas we've been working with z-scores, normal models, and so on. Number 4, middle of the page. What we're investigating, students, is the behavior of p-hat, the sample proportion, when we take repeated samples. This is the framework for the rest of the semester. Remember, we're investigating that hunch that at Cecil more than 20% are smokers. At this point, are you convinced? If you look at these numbers, could you make the conclusion that more than 20% of us are smokers here at the college? I mean, I think it's certainly pointing in that direction. Since we'll only take one sample in practice, we won't take 10 or 100 or 1,000,000, we'll take one, we need to understand the variation and the behavior of this number p-hat, the statistic p-hat. And if we know the variation and behavior, then we can make the most out of our one sample that we'll collect. In reality, this is what would happen. You take that one, you don't take 9 more. You take one and you use this to make your decisions. Okay? At the bottom of the page, number 5, where should all the sample proportion values in the box center around? In other words, what should the mean be? All right? The mean should be, if I took the time to count up the greens in that box, and I learned that, hey, in the box, it's exactly 30% greens, shouldn't these bounce around 30%? Sometimes you might get exactly 30%, sometimes more than 30, sometimes less, but on average, if the true proportion is 30, shouldn't these bounce around 30? That makes sense, right? So, where should the sample proportions be? Where should all the sample proportion values in the box center around? These should center around the actual or the true population proportion of greens. That number, that's the number when Kim drew the population picture, that's that P number, that's that unknown percentage. P, population proportion, is the parameter. This would be that number P. And again, P is unknown. I never took the time to count up the beads in the box and figure out the exact proportion of greens. Okay? If you draw a little picture, somewhere here is going to be P. That's the true number. And when I take samples, you know, sometimes I get real close to P with my p-hat, or maybe I get exactly, or maybe a little bit bigger here. Maybe sometimes we get something that's really high, like we got a 38%. Maybe sometimes we get something that's really low, right? Maybe I got a 22% smokers that'd be down here. And that data would just, here's all those sample proportions. I'm not trying to match this up to the numbers I actually selected. I'm just saying that, look, if the true number, whatever it is, 30% for example, when I take repeated samples, it's going to bounce around it, but it should sort of balance here at the true number. Okay? In other words, what should the mean be? The mean should be the true proportion. Okay? Now, by the way, if I took this 30%, this p hat, I would not know if I hit the target exactly. I would not know if I was below the target or above the target. We'll never know that. Okay? But we expect it to hit the target. So that's what the mean is, expected value. Remember, we've used that word before. All right, at the top of the next page, at this point, we'll do some more simulations in class, probably on the computer to speed it up. Takes a little time to even collect those scoops of beads. At this point, take our word for it that if you kept scooping paddles of beads, kept keeping track of the numbers, a dot plot or a histogram. So graph these. With 10, you won't see much. Do it 100 or 1,000 times. That histogram is going to start to look pretty darn unimodal and pretty darn symmetric. And you already see the punchline in the notes. I'll reveal it here on the screen. So here's what I did on the computer. I programmed StatCrunch and I said, what if I had 20% smokers? Because that's that national figure. Let's start at 20% and do a simulation. I generated, looks like 1,000 scoops of beads. I calculated p hat again and again and again, right? So just imagine the computer is just like calculating p hat, 1,000 of them. We did 10. Here's 1,000 dots on the dot plot. And if I gave you this dot plot and I say, hey, which model looks like the appropriate model? At this point, we would all say, hey, that looks normal. It's unimodal and symmetric. What are the features of a normal model? Most of the data is very close to the center, right? Most of the data is very close to the center. And because I programmed StatCrunch to be 20%, most of the data is very close to 20%. Now, I'm not saying at Cecil College it would look like this, because I think more of us are smokers. But when I programmed it here. Occasionally, I get something way out here in the tails, right? And you saw that on our simulation with the beads. And occasionally, I get something way down here in the tails. But those are sort of unusual. Most of the data is in the middle. What model would you use for this data? Of course, you use normal model. Better at this point, right? When working with this model, the normal model, what are the two model parameters that we need to know? For normal, always two things. Mean, standard deviation. We would need that mean. Remember, the symbol is mu. We would need standard deviation. And remember that that symbol is sigma. Okay? So let's think about it in the context of this theoretical distribution. Let's get that mean. Let's get that sigma. All right. So flip that page. 7 and 8 here, last page of this video. Number 7, so under certain conditions, and Kim Shepard will talk about those conditions in the next video. This just doesn't always work. We need to check some conditions first. The sample proportion will be well modeled by a normal model. So, what the heck is the mean? The mean of the sampling distribution model for the sample proportion, quite a mouthful, but it's correct terminology, is going to look like this. You put mu, and the mean of what? So down in the subscript, you put a little p hat, and all this means is the mean of p hat. There's no calculations here, it's just the symbol. All right? The mean of p hat turns out to be p. That's the easy one, right? And I've got a note here. It's in my notes it says our repeated samples will always balance around the actual proportion, right? This is saying that we expect p hat, the mean of p hat, we expect it to be, whatever the true proportion of greens is in the box, I expect that to be the mean, And that makes sense, right? Let's do standard deviation. Not so intuitive, but number 7, we need that standard deviation of the sampling distribution model. And remember, it's normal. The symbol looks like this. Sigma with the subscript p hat. This just says the standard deviation of p hat. All right, equals. There's a formula for this one. Big square root p times 1 minus p all over n, and make sure the whole thing is under the square root, not just the top part. Okay. This p, again, is the true proportion of, say, smokers at Cecil College, or the true proportion of green beads in the box. Theoretically, and realistically, I won't know that number. Now, in a classroom setting, maybe you'll be told it so we can learn about the distribution. But in reality, this number you won't know. Now, I do know the sample size, right? I took 100, so n equals 100, I know that. And maybe if I assumed at Cecil College 20% were smokers, I would start with the 20% here, and then figure out what this standard deviation. Okay? Sometimes in the notes, we might do a little shortcut. I tend not to do that, but in case maybe your other instructors, or if you see it in the note packet, sometimes people use the letter Q for 1 minus P. So if you see P times Q here, it's the same thing. It's just 1 minus P. All right. So to wrap this one up, now at Cecil College, we do not know the true proportion of smokers. Remember, that's unknown. We're going to assume that it's 20%. That P is the 0.20. Assume is underlined, like I'm making an assumption here. I don't know if it's a good or bad assumption, but I'm making that assumption. We might change our mind. Remember, we'll take one sample of data, and if that data is compelling enough, like let's say we take one sample and we get 30% smokers, is that going to change our mind about our assumption? Okay? Presuming it's 20%, what's the correct model we can use to model the sample proportion? All right, so the model is going to be a normal model. Take our word for it now. Kim's going to give you the conditions to check in the next video, but they're met, so it's a normal model. You need those two parameters. You need the mean of p hat, and the mean of p hat is easy, p. So, under our assumption, the mean of that model will be 20%. Standard deviation. Under our assumption, sigma of p hat is going to be big square root p times 1 minus p all over n. Plug the numbers in. So p is 0.20. If 20% are smokers, then 1 minus p, 80% are non-smokers. And remember, we took samples of size 100. I think this is 0.04. Let me take a peek here. Yep, 0.04. So to wrap this up, under our presumption, 20% smokers, the model that we'll start with, to model p hat, we'll center it at 0.20, 20%, and there's a standard deviation of 0.04 or 4%. That 4% should make sense if you think about how our samples danced around. Does 4% make sense in the context of all those scoops? Sure, right? A lot of 30% and some 36, 38, 22, 23. So this is reasonable. And this is our guess until we collect the data and maybe change our minds. All right, a lot to handle in this. This whole video is just, it's very abstract. But this is the theory that we're going to base our confidence intervals and our hypothesis tests, which is pretty much the topic of the entire rest of the course. So, watch it again if you need to. We'll review this in class, and we'll see you there. Thanks.